So this is part 3 of the atom test, which was really about quantum numbers. The first question reads, if two electrons are in the same orbital, they must have how many quantum numbers in common? So I'm going to take a look at an example, and we'll just do a simple one. We will do, how about sulfur? So sulfur has 16 electrons, and its most common isotope has a mass of 32. So if we write the electron configuration for 16 electrons, we'd have 1s, which would hold 2, and then a 2s, which would be 2, and then a 2p, which would hold 6, and 3s would hold 2, and then the 3p would have 4 for sulfur, because 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 4 is 16. Then if we draw in the actual orbitals, remember all the s's have 1 orbital, all the p's have 3 orbitals, all the s's 1, all the p's 3. And then if we went up to d orbitals, there would be 5, and f orbitals 7. All right, so putting in the electrons for sulfur, we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, so this question says 2 electrons in the same orbital. So I'm going to pick, by the way, 1 is not the correct answer. I'm going to pick this orbital right here. The one I'm pointing to right there. So the N, L, M, and S quantum numbers. Okay, so for the green electron, we'll just do that one, N would equal 3 because it's in the third energy level. L would equal 1 because it is a p sublevel. And you'll remember from previous videos that the p sublevel has an L equals 1 value. Then the M values would be -1, 0, 1. So for that particular electron, the M would be -1. And if we say that one was that would actually, the way I drew it, that was the second electron in, so that would be the -1/2 spin, which means it's spinning counterclockwise. And again, these two are kind of subjectives because it depends on convention, but we agreed that -1, 0, 1 would be the order we'd use, and then the first electron in would be a +1/2, and the second electron in the orbital would be -1/2. So now this would have been the first electron, the way I drew them, single, single, single. So for that electron, n would equal 3, still in the same sublevel, L equals 1, still in the same orbital, m is -1, but the s value has to be opposite if they're in the same orbital. All right, so now how many quantum numbers did they have in common? 1, 2, 3. So the answer to that first question would have been 3. Okay, this is the electron for antimony. So we want to know which one, electron configuration for antimony, Sb. Sb has 51 electrons. Which set of quantum numbers describes one of the orbitals in the 5p, and L is L, of course. So in 5p, n would equal 5. So that eliminates the first answer. L would equal 1, so that's the answer. Because that would have been a 5d, and that would have been a 5s. Two electrons that have the same value of N, L, and M must be spinning in opposite directions. This was an example of that. N, L, and M were the same. They had to be spinning in opposite directions. So the quantum number L has a value of 3. If the quantum number of L has a value of 3, which one of the following energy levels could be represented? Well, let's go back and look at our examples for that. So if L equals 3, you have to go back. L can go from 0 to n minus 1. 0 to n minus 1. So if L equals 3, then we know n has to equal at least 4. It could be 4 or more, but there is no L equals 3 if n equals 3. See, if n equals 3, then L could be 0, 1, or 2. But if n equals 4, L can be 3, 2, 1, or 0. 4 values. So the only answer here that allows for an L equals 3 value would be the fourth energy level. So if you wanted to describe a single specific electron, you have to know what N, Here they are, N, L, M, and S values are, so that would be 4. And it says, the Pauli exclusion principle says that no two electrons in the same atom can have identical quantum numbers, but how many could they have in common? They could have 3, as in our previous example. So these two electrons have 1, 2, 3 in common, but not the 4th. All right, so this one, last electron has the following quantum numbers: N equals 3, L equals 2, M equals 2, and I'm going to kind of draw that out so we can see what it looks like. So if N equals 3, get over here where we can see, so N, L, M, S. N equals 3, L equals 2. So if L equals 2, that's a D sublevel. All right, so, and the M value is -2, and S is -1/2. All right, so let's talk about, this is a 3D sublevel. So this element's in the 3D position. I'm going to draw the orbitals out for the 3D. There will be 5 of them. -2, -1, 0, 1, and 2. All right, so by convention, we're going to go negative to positive. And we said the second electron would be the negative value, the first would be positive. So you'd have so the electron that we're talking about would be this green electron there. So he's in the third energy level, D sublevel, first orbital, and a -1/2 means he's spinning counterclockwise. He's the second electron in that orbital. So there's 6 in the 3D. So then if you go back to 3D6, let's pull up the periodic table, 3D starts here, so it'll be 1, 2, 3, 4, 5, 6. 3D6 is iron. So we're hoping that iron is an option, and look, it is. Okay, if the quantum number M has a -2 value, what sublevel can it not be in? It has to be at least in a D or an F. So it can't be in a P, because if P has an M is L equals 1, and M goes from -L to +L. So if you have L equals 1, M can be -1, 0, and 1. So there's no possibility for a -2. So you have to have at least an L value of 3 for M to be -2. So F, G, or D all work. Okay, this one, the last electron here, this is the set of quantum numbers for the last electron. So if N equals 3 and L equals 2, that's a 3D. So D sublevel. And here's one more of those where you try and identify the element. So you have N equals 3, L equals 1. Let's draw that one out. Okay, so we have 3, L equals 1, M equals -1. I'm just carrying these down here, like that. And S is +1/2. So this is 3p, because L equals 1 is a P sublevel. So here are your 3 orbitals. -1 is this one. +1/2 is the first electron in. So that would be the complete P sublevel for this particular element. So there's 1 electron in the P sublevel, in the 3p sublevel. Then you go back to your periodic table. Here's 3p. There's 1 electron. So the atom is aluminum. So we hope aluminum is a choice. And it is. So that would be the end of that little section of the test.